All right, so we have a bit of material to cover today, so I'm gonna have to start just about now. All right, so we have 118 people. It's a decent amount of number, so I think we can get started. All right, so welcome to week 7 of AI504. So this is the last week before we get into the first project number 1. So we'll talk about that after this class, at the end of the class. So as of now, so already, project number 1 will be generating images using GAN and ConvNet, in a combination of the two. So please pay attention. If you don't know what ConvNet is, I'm kind of guessing that a lot of people already know what ConvNets are, but still, like, if you don't know what it is, please pay close attention to what I say today. All right, so today's topic. So CNN, obviously, we're going to talk about CNN and the core components of CNN, which are the filters or kernels, strides, and pooling. Oh, actually, it's working out pretty well. Okay, cool. And some of the side stuff like 1D CNN, 3D CNN, and training techniques. These are kind of like old techniques, like BatchNorm and Dropout. They are no longer like heavily used anymore, but still they have been a very core part of like deep learning research advancement. So we'll touch upon that only slightly. And then some of the CNN architectures, VGNet, Inception, these are like really old stuff. But ResNet, the concept of residual connection still lives on till today. So we're gonna have to look at this a little bit more in detail. So that'll be it. So ConvNet, or convolutional neural network, CNN. So this is inspired by how human brain interprets or processes visual signal. So there's a visual receptor here, which receives like photons, and then it converts the photons into electrical signal, which goes to your brain. And it looks like it follows this way, like this here. And along the way, there's like a hierarchical structure as to how brain like interprets the electrical signals. So you start with a very simple stuff, like low level information, and then you aggregate it, and then you aggregate it, and then you aggregate it, and then finally you, for example, you start with like edges and lines, like the contours, and then you build it up to a bit more high level information, which is a shape and objects and faces. So that's how you recognize people's face, like, or that's what we've like found out so far. So there's like different brain parts or visual cortex. So just like that, so based on that theory, so there's a ConvNet is kind of like built upon this theory or inspired by the theory. So you have an image, and the very first ConvNet, or I'm not sure if it's called LINET, why it's called LINET 5, maybe there's like 5 layers. So the very first ConvNet by Yanle Kun, Yoshio Benjo, Leon Buteau, I'm not sure who this is. Anyway, so like very old paper, it's like 1998. So you start with a very simple, low level, like not simple, but like low level information, which is like pixel level information, and then you build you process the pixel level information into like higher level stuff, and then higher level stuff, and then finally you try to figure out which alphabet this is, like whether it's like A, B, C, D, E, F, G. That's like very old stuff, like 1998. So the theory or the concept of convolutional neural network has been around for like 25 years now. So, but the first breakthrough that the first like birth of deep learning, or the thing that initiated the whole deep learning in 2012. So sorry, 2012 is something called AlexNet. So this is the first paper, the first like well-known deep learning architecture. Kind of like you can see this as like a very first deep learning architecture by Jeffrey Hinton and Susskiver, who's like the OpenAI guy now, and Alex Krichevsky. So this has a pretty like not convoluted, but a rather complex architecture. You start with a like input 2 to 4 by 2 to 4. I guess this is an image like 2 to 4 is a height and width, and then the 3 dimension is the RGB, and then you have like two streams of information processing channels, and then you aggregate it at the end, and then you do a 1,000 way classifier. So this is an ImageNet classification. This model solves ImageNet classification challenge. So it has 1,000 output classes. And this is still old stuff. This is like 11 years ago, right? So modern convness can do way more than just classification. It can do like information retrieval. If you are familiar with like Clip from OpenAI, it can do like retrieval very well. And there's like object detection, object segmentation, which is a little bit different. So object detection usually use a rectangle, like square boxes to identify stuff. Segmentation is a bit more like pixel level. You can see like you can actually annotate pixels into different classes, and obviously you can do like captioning, image captioning. Given an image, you write a simple description of what the image is about. It can do style transfer, which is also like quite an old technique nowadays. And well, I haven't put it here, but like if you're familiar with like diffusion, like DALL-E 1, DALL-E 2, DALL-E 3, like stable diffusion, now you can just generate whatever image you want just by putting text into the model, like you can probably like generate this as well, like three houses drawn in a Van Gogh style, something like that, So if you're interested, I mean, we're going to talk about diffusion anyway. So, but if you're interested, you can try it out on the internet. So what is CNN? So we're going to talk, I mean, CNNs are, I guess some people would say that transformers are taking CNN's place when it comes to image processing or image encoding, because nowadays people frequently or often use vision transformer rather than convnets, but still like convnet has its uses. So, and it's a very important part of like deep learning history. So you should pay very close attention to how it works, the inner workings of CNN. So we'll start with a fully connected layer, which is not CNN. This is just MLP, like fully connected layer. And if you think about stretching or flattening a 2D image having 32 by 32 dimensionality, height and width. 3 is the RGB channel. So it's your image has a 32 by 32 by 3, and you can flatten it to 3072 by 1. So you have an image, and then you flatten it like this, So this will be your input. If you think about encoding or decreasing, like downsizing the dimensionality of your input from 3072 to 10, then what you would do with fully connected layers, you would employ a matrix that has a size 10 by 3072. So which would be like very, very long, like this. It would look like this. Like this would be 3072, and this would be 10, right? And so you multiply it, and then you would get 10 by 1. So that would be fully connected layer. So each dimension or each value in your output, which is 10-dimensional vector, or we call this activation. So each value in your output is determined by what? It's determined by, do we have it here? Yeah, determined by the result of taking a dot product between a row of W. So this, like here, like a row of W, or actually this will look like a single row here. Single row here will be doing a dot product with this guy, and then it'll give you a value here. Actually, let me, like this. So this is 10. This is 3072. And then each row, there will be each row. And so the first row will correspond, first row with this guy, do a dot product, and it'll go here. Second row, a dot product with the input, it'll go here, like this. But as opposed to that, convolutional neural network works in a different way. So it preserves spatial structure, which means that you don't flatten your image like this when you encode your image. If you're using fully connected layer, you have to flatten it so that you can multiply it with a matrix and then get a 10-dimensional output. But in convnet, you don't flatten it. You actually take it as is. So how it works is you use something called filter, or is also known as kernel. So you filter, kernel, they're the same thing. And a filter can have a 5 by 5 by 3 dimensionality. And if you're familiar with like digital signal processing, like DSP, then you know what convolution is, right? You just slide a filter across your input. And in DSP, you would do it on a one-dimensional signal, but this is two-dimensional signal. Actually, this is three-dimensional signal because it's 1, 2, 3. But still, what we usually call images a two-dimensional information. So you convolve your filter across the image. So and the important thing that you should note is that if the channel, the three-dimensional channel, RGB channel here, given that, your filter also has to have the same number of channels. So if you look at here, this will be 5 here, and this will be 5, and this will be 3. So your filter channel, the size of the channel in your filter, has to be the same as the size of your channel in your input. So this is, if this is 3, this has to be 3, right? So what happens here? So what happens is that if you have a single filter that is 5 by 5 by 3 size, and you put it on top of 32 by 32 by 3, so it'll look like here, right here, right here. And what happens is you just do a dot product between the filter and the small 5 by 5 by 3 chunk of the image. So here, so there, for example, let's say that this has like value like 0, 1, 0, 1, 1, 0, sorry, 1, 0, 1, 1, 0, 1, 1, 1, 0, something like that, 1, 0, 0, 0. You can think of this as like a black and white image, and there's only one, the pixel value is either 0 or 1. So, for example, if there was a patch right here, which is 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, is it maybe one too many ones? Yeah, and 0, 0, 0, 0, 0, something like this. And then if your filter has a value, let's see, 1, 1, 1, 1, let's blow it up here. 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, and 0, 0, 0, 0, 0, and there will be 2 more rows here, but I'm just going to skip that. So if you do it, and there should be 2 more rows here. But so anyway, so if given this, then what you do is you just do a dot product between this guy and this guy. And I've just actually omitted the 3 dimensions here. There should be 3 dimensions, but I just skip that. So what happens is you do a dot product between this, which means that you multiply this guy, the first 0 with this guy, the second 0 with this guy, and the third 0 with this guy, and you keep doing it for all the values here, all the values here, and all the zeros here, and you simply just sum them up, which is exactly just a dot product, right? So that's what's happening here. And actually, yeah, we've omitted the bias, but there's always a bias. So far, no problem, right? This is very simple stuff. So you do this starting from the top left, and then you slide it, and then you slide it, and when you reach to the end, then you go to the next row here, and then you slide it. If you're done, you go to the next row here, and then slide it. And every single time you do a dot product, you do a dot product here, you do a dot product here, dot product here, and here. You keep doing it, basically. Keep doing it. So when you've done the entire thing, when you've convolved your filter across the entire input image, like in this manner, basically you just do it, slide it across the entire thing, then you are left with a 28 by 28 by 1 output, or activation map. It's the same thing. So your output, see, the operation, convolution operation will give you, so given a 32 by 32 by 3 image and a 5 by 5 by 3 filter, will give you a 28 by 28 by 1 output. Okay. So far, no question, right? Very simple stuff. And if you use another filter, so the first filter was the blue filter, right? It's the blue guy. And oh, actually, so what's happening here is this is a scalar value with a single filter on a like this patch here is a dot product. So the dot output of the dot product is obviously a scalar value, right? So it's a scalar value that should be like here. So if you start from the top, then that scalar value will be the very first value here, right? And then if you move right side, then that value will be here, right? And that's how you get the entire activation map. If you use another filter, which is the green filter now, the second filter, then you would get another activation map, right? So the output or the activation maps, the number of activation maps is determined by how many filters you use to do convolution. So if you use 2 filters, you get 2 activation maps. If you use 3 filters, you get 3 activation maps. And in this case, I guess we are using 6 filters. So 6 filters, 6 5 by 5 by 3. We forgot the 3 here. 5 by 5, 6 of them. So 5 by 5 by 3 filter, 6 of them will give you 6 dimensions on the channel and 28 on the spatial dimension. Okay. No biggie, right? So if you do a 32 by 32, so you start with an image that has 32 by 32 by 3, you use 6 filters where each filter has 5 by 5 by 3, then you would get 28 by 28 by 6. So this 3 corresponds to this 3. This 6 corresponds to this 6. And because we are using 5 by 5 on 32 by 32, you get 28 by 28. Okay. If you the next time, for example, given this activation map, given this, if you use 10 filters, where each filter has 5 by 5 by 6, not 3, 6, because your input to this convolutional operation, this conv operation, has 28 by 20 by 6 channels. So that's why your that's why your filters channel is also 6, because it matches, right? 3 matches, 6 matches, and you're using 10. So there will be 10 channel output, right? So far, so good. I think there was a question. Why does the result have 28 by 28, not say 27 by 27? We'll get there, but if this is 32 by 32 and you use 5 by 5, then what? This is like, yeah, this is, I can't do the arithmetic. So you start. So you start with one from 5, and then you'll end with 27 to 32? Is it right? Actually, 28 to 32. 28 to 32. So you start with 1, 5, and you'll end up with 28, 32, right? So that's why you have 1, 28. So it's why 28. Hopefully this makes sense. It's just simple arithmetic. Right. So again, when you do another convolution operation with input 28 by 28 by 6 and filter 5 by 5 by 6, and 10 of them will give you 24 by 24 by 10. Right. And you can see non-activation, non-linear activation put in right between like the convnets, like this. So the typical operation is you do convolution and then you put some non-linear activation function, which could be sigmoid, which could be tanh, ReLU, whatever you want. So ReLU, another conv, then ReLU, another conv, then ReLU, so on and so forth, until you have enough number of layers. So the receptive field, another question. I'm wondering the reason why many filters are used. Why many filters are used? Are you asking why we're using 5 by 5 by 6 instead of 5 by 5 by 3? I just told you that this number should match, like here and here. The number, the channel dimension of your input, this is the input to this conv, right? The channel dimension of your input should be, or actually the other one, the channel dimension of your filter, should be the same as the channel dimension of your input. So 3, 3, 6, and 6. And how many filters to use? In the first layer, they use 6 filters. In the second layer, you use 10 filters. That's hyperparameter. Like you can use 32, 64, you can use 16, 8, it's up to you. The important thing is this has to match. Right. So we come now to the concept of receptive field, which is a very important concept in CNN. So repeated conv layers increase the receptive field. What is a receptive field? Receptive field is when you stack enough number of convolution layers, then at the top layer, a single value will be representing a large patch in the input. So here, for example, when we have 5 by 5, channel, 5 by 5 filter or kernel, which would be which would be downsized into a scalar value, which would correspond to here, some value, scalar value here. And then you collect another 5 values like that, another 5, 5, 5, 5, like this. 2, 3, 4, 5. 1, 2, 3, 4, 5. And then there will be another 5 by 5 filter, which will convert it into a scalar value here, which will go here. So that means that this single value will be looking at this single value will be looking at this patch, where each single value will be looking at this patch. So which means that, recursively, we'll even be looking at even larger patch. So a single patch will look here, like here. So in the end, the input layer, it'll be a very huge patch. So that's what's this is happening here, like here, here, and here. So we would like to have the last layer to have a large receptive field, so that it can, if this can look at large receptive field, then it'll be looking at a large, it'll be taking in large information, basically a large chunk of information from the raw image, which would lead to a better informed decision. So it would be better to have a larger receptive field. And so the important concept here is that 3 layers of 3 by 3 filter has the same receptive field as a single 7 by 7 filter. So if you count the number of pixels here, there's like 1, 2, 3, 4, 5, 6, 7, 7 here, 7 here. That's when you're using a single 7 by 7 filter, like one filter which has a dimensionality of 7 by 7, right? Versus employing 3 by 3 filter here, 3 by 3 filter here, 3 by 3 filter here. So 3 consecutive filters where each filter has 3 by 3 receptive field will lead to, on the final layer, having the same 7 by 7 receptive field. It's like the same thing. Having a single layer of 7 by 7 filter will have the same receptive field as having 3 layers of 3 by 3 filters. And the good thing about having this instead of this is that it requires less params. So if you do 3 by 3 times 3, because this is the filter, and this is the layer. This is number of layers. That's what? It's 27, right? 27 versus 49 here. So it's using less number of parameters. Because I guess like a filter, the values, the values inside the filters are all learnable parameters. I forgot to say that right here. Yeah, here. The values here, the 5 by 5 by 3 is exactly the number of learnable parameters. This is what we are learning. These values, like 5 by 5, which is 75. So we're learning 75 parameters, which is exactly this filter's value through backpropagation. So I forgot to mention that. And that means having 3 layers of 3 by 3 filter will require 27 parameters as opposed to 49 parameters. And this guy still has the same size receptive field as this guy, so which is more efficient because we're using less parameters, right? So that's one thing. And it is deeper. So having 3 layers of 3 by 3 filter, which is exactly requires 3 layers. This guy is only 1 layer. So, and it says that it's deeper is like a good thing. So bonus question. Why is it a good idea to have a deeper layer than a single layer? Non-linearity. That's a kind of like a semi okay question, semi okay answer. Yeah, more parameters is not a good answer. So it's I guess non-linearity is like a yeah, it's an okay-ish answer. It's an okay-ish answer. So non-linearity is the spirit of deep learning. As I've already showed you guys how a nonlinear activation function allows you to warp or distort the latent space. And that's where the power of deep learning comes from. It's the warping, it's the power to warp or distort the latent space so that you can do whatever you want, whether you can like draw a hyperplane that like a good decision boundary or whatever you want, right? So having more layer means you have more chances to warp the spaces, warp the latent space as you would, as necessary, as much as you want, basically, as much as necessary to fulfill your objective or your goal. So that's why it is usually it's usually a good idea to use like many layers, but it can lead to overfitting, obviously, right? All right, so moving on. So if you visualize what kind of values or patterns that each filter learns in each layer, it looks like this. So this is something called VGG16, which is a very old architecture, like way before, like, I don't know, like ResNet. So low level features, it's the patterns. So this is a filter. So I guess this is like a 3x3 filter, like, or maybe 5x5. You looking at the pixels, like looking at pixel 1, 2, 3, 4, 5, 6, 7, maybe like 7x7 or something. Anyways, this is just some filter, right? So if you look at the filters, in the first layer, the patterns are a little bit, like it's looks like this guy is focusing on horizontal, vertical like contour or boundary, and this guy's focusing on red color. This guy's focusing on magenta color. This guy's focusing on green color. This guy's focusing on, I don't know, some diagonal line, something like that. And then if you go to the second layer, or is this the third layer? I think this is the third layer. Like if you go to the third layer, the patterns are a little bit more, complex. And if you go to the fifth layer, it's even more complex. And that's how like, just like how human brains interpret like electrical signal to visualize stuff, it's kind of like the same deal. Like you go from the lower layer to the upper layers, it becomes the filters become more, or the signals become more like complex. And the same, another example. So this is, I'm not sure which layer this is, but this is just different, like 32 different 5x5 filters. So there's like 1, 2, 3, 4, 5, all the way to 32 filters. And each filter will obviously give you one activation map, right? Because the number of activation maps correspond to the number of filters you're using, right? So there should be 32 total activations here. And you can see that each filter will give you different activations. So this guy will give you this activation function given this input. So this is the input and this is the output. And this guy will give you this output. So each filter will focus on different stuff. Like it seems like this filter is focusing on headlight. I think this is a car. So headlight, I don't know. Like, I'm not sure what this guy is focusing on. Anyway. Right. So how typical like convolution neural networks are, like structured. It usually goes through a conv, nonlinear, occasional pooling function, and conv, nonlinear, pull, like repeat that for several times. And then after that, you do some kind of pooling here to do a final classification, like ImageNet classification, Cypher classification, MNIST classification, whatever classification you want. So this is a preview. So yeah, we've looked at the spatial dimensions, and we've already established that given 32 by 32 by 3 image with 5x5 3 filter will give a 28 by 28 by 1. So closer look at spatial dimensions. So let's make it simpler. So we have, instead of 32 by 32 by 3, we have just 7 by 7 by 1, and we assume 3 by 3 filter. And what happens is with this, like from here, the first convolution, second, third, fourth, and fifth, right? So there should be like the output dimension should be like 5 by 5. So 3 here, and that's how you get 5 by 5 output, because you have 1, 2, 3, 4, and 5, right? So it means that inevitably, when you use 3 by 3 filter, your output, your activation map will be smaller in spatial dimension than the input, because your input was 7 by 7 and your output is 5 by 5 because you're using 3 by 3 filter. So what happens if you use stride 2? Stride is how many like pixels you skip to the next place. So here, stride 2 means you skip 2 places. So you go here, here. Not so previously you were from here and then you move here. If you're stride 2, then you are here, and then the next time you are here, right? And the next time you will be here. So that means that your output will be 3 by 3. So your stride also determines the output size. Your filter size and your stride size determines the output size. Okay. What happens if you're using stride 3? Stride 3 would be, it doesn't fit because your stride 3 is like here, here, and then you have nowhere else to go because you're like moving outside. You're moving outside your image, your boundary, your input boundary. So it doesn't fit. So you can't use 3 by 3 filter on 7 by 7 input with stride 3. This doesn't work. But what you, so yeah, there's like a very simple like equation which you can use to determine or calculate the output size, but it's just simple intuition. So what you can do instead is that if you don't like your output size being always smaller than your input size when you're using a 3 by 3 filter, even with stride 1, even with, what you can do is you can use padding here. Like you can pad your original image is this. This is your original 7 by 7 image. And then you pad, you encapsulate you surround your input image with zeros here, with zeros, so that your input is now 9 by 9, not 7 by 7, 9 by 9. And on 9 by 9, when you use 3 by 3, you will have a 7 by 7 output. So that's how you preserve the dimensionality between, you keep the same dimension between input and output by using padding, the padding. So obviously, yeah, like I said, you get 7 by 7 output. So obviously, when you use a larger filter size, not 3 by 3, but when you use 5 by 5, for example, then you would need a larger pad. You would need two layers of padding, like here, like, how do I draw this? Like there should be another like layer, another like zeros here, zeros here, like this, like this. Yep, like this. So that your 5 by 5 filter will give you still 7 by 7 output. If you're using 7 by 7 filter, then your pad size should be 3. So if you want to preserve the dimensionality between input and output, you should use padding, but the size of the padding should be correlated with the size of your filter, basically. Question: to match 3 by 3 to 7 by 7, except for padding, can I throw the last row or column away? What does that mean? Match 3 by 3 to 7 by 3. I don't understand what you mean, Shang-Chi. Yeah. If your input size is 7 by 7 and you're using 3 by 3, then you have to use padding in order to preserve this dimensionality. Yeah, I don't know why you would discard stuff. If you discard stuff, then your input should be even smaller. Yeah, I'm gonna turn to another question from Hewan. Why is it important to preserve dimensionality? That's it's so if you want to use like many layers to increase the representation power of your model, and each layer decreases your input size, then there are only so many layers you can use. 혹시 이해되셨나요? 레이어를 쓸 때마다 인풋 사이즈가 이 이미지가 줄어들면은 내가 100레이어를 못 쓰잖아요. 100레이어를 쓰고 싶어도. Does that make it clear? 제가 방금 전에 얘기했죠. 왜 7 by 7 하나 대신에 3 by 3 3개를 써야 되냐 얘기했잖아요. 왜 딥해야 된다. 왜 딥해야 되냐? 네, 이해되셨죠? 네, 넘어가겠습니다. Right. So where are we? So example time. So some simple question. I mean, there's already an answer in the next slide. So you should not. I mean, if you want to practice, you shouldn't look at you shouldn't look at the next slide. But so if your input image is 30 by 32 by 30 by 32 by 32 by 3, and you're using 10 of 5 by 5 by 3 filters with stride 1 and ped 2, then what would be your output volume size? Which would be, you're using 5 by 5 with ped 2, so your dimensionality will be preserved, and you're using 10 filters, so the output size will be 32 by 10, right? So yep, 32 by 32 by 10. Number of parameters in this layer. So what is the number of parameters? So I said that the number of parameters is exactly the size of your filter. So the size of filter is 5 by 5 by 3. So 5 by 5 by 3. And we're using 10 of them, right? 10 of them. So which one is 750? 750, right? 750. But we forgot about the bias. So if you remember the bias, then there's one bias per filter. So there should be 10 biases because there are like 10 filters, right? Yeah, exactly, the bias. So it's 760 is the answer, 760. So if you think about, like, if you think about how this is, if you compare this with fully connected layer, CNNs are way more efficient. It uses way less number of parameters to, encode images, and but it has a very strong assumption. Strong assumption meaning that, what is the strong assumption that we're using in CNN? It's that when you're using a filter, it means that only the information in this region, in this neighborhood, matters. You don't need to look at, so you only need to look at this patch one at a time. So it means that anything outside this patch, you can wait until you go to the next layer where your receptive field becomes larger. So immediately what you care is only your neighborhood. So it's a local dependency. You only care about the local information. So that's the strong assumption that we're using, or we're depending on when we're using convolutional neural network. So it means that you shouldn't use CNNs on data where there is very weak local dependency and very large global dependency. Okay, hopefully this makes sense. So the summary, yeah. So summary, convolutional neural network, there's a lot of parameters such as number of filters, how many filters you want to use, the size of the filter, the stride, how many pixels you want to skip when you're convolving, and the size of the zero pad. So yeah. So KFSP, or 4 parameters. Right, and so that was the gist of CNN, and there's something called one by one convnet. So 1 by 1, which means that your filter size is only 1. So so far we've used 3 by 3 or 5 by 5, but we can also think about 1 by 1, which would amount to actually. So if you think about using 1 by 1 convolution here, then you would have to use 1 by 1 by 64, because there's 64 here, 64 here. So it would look like a very long. This is not a good drawing. Like this. So it's 164 here. Very like a long fiber, basically. So if you use this kind of 1 by 1 con filter, and 32 of them, they're using 32 of them, so it should be 32 here, 64, 64. It means that your dimensionality, your spatial dimension, wouldn't change at all, even without all the padding, because the padding is required when your filter size is larger than 3, 3, 5, 7, then that's where you use padding size 1, 2, 3. But when you're using 1 by 1, there is no, you're not modifying, you're not changing the dimensionality. So there's still 56, 56. It's just that you're using 32 filters, so 32. So where would you use this kind of weird 1 by 1 convolution, which is when you want to manipulate the channel size. So you simply want to just downsize your channel, 64 to 32. Then you can use 1 by 1 convolution neural network. Question: how do we decide what kind of filters to use? Actually, we use 3x3 mostly. Like we don't use 5x5 or 7x7. We mostly stick to 3x3. Is it like a linear layer? I'm not sure what kind of question that is. Is it like a linear layer? 김현진님, 패딩하는 이후에 레이어가 깊어짐에 따른 사이즈 유지도 있지만 보더 부분의 정보를 좀 더 사용하게 되는 효과도 있을까요? 보더 부분, 패딩은 다 0으로 채우기 때문에 보더 부분을 어떤 말인지 이해됐습니다. 보더 부분에 조금 더 집중해서 사용할 수 있겠죠. 그게 뭐 성능에 도움이 될지 안 될지 모르겠지만, 뭐 보더에 정보가 집중돼 있을 확률이 뭐 얼마나 있을까요? 보통은 이제 이 사진의 가운데에 인물이 있든 뭐 물체가 있든 그렇지 보더 부분에 뭐가 일부러 막 위치해 놓게 사진을 찍진 않잖아요. 그렇기 때문에 보더의 정보를 열심히 활용하는 게 얼마나 도움이 될지는 잘 모르겠습니다. Question from Tom. Can it learn patterns across channels as well? Can it learn patterns across channels? Actually, yes, because your filter should always have the same dimension or same channel dimension as your input. So it is actually using all the channels at the same time. It's looking at all channels at the same time. It's not looking channel by channel independently. Hope that answers your question. From Kim Gian, is there a reason for the edge padding to be 0? Actually, no, it doesn't have to be 0. It could be any arbitrary value. You'll see in a minute, actually. If you look at the PyTorch conv2d API, it actually lets you use other values than 0 for your padding. Yeah, you can use extrapolation. Yeah, could be a good idea, right? So as I said, yeah, it's just one dimension at a time. So you're just simply resizing your channel. So right here, so example in conv layer in PyTorch. So there's something called torch and then conv2d, and you'll see all the parameters that we've talked about so far. The in channel is the channel dimension of your input. Out channel is how many filters you're using, and the kernel size is either 3, 5, 7. Stride is stride. Padding, you can use 0, but you can use other values. You could use like 1 or 10 or like -1, whatever value you want. Dilation is something that we haven't talked about, but we don't have time to talk about dilation or groups for that matter. Bias, usually true because we want to use bias. And padding mode, zeros, I guess there are other ways to use padding. Right. So you will get to use ConvNet in this Thursday's practice session. So we haven't talked about pooling yet. Pooling is what or was or maybe still is like a very important part of convnet. So pooling is simply just a dimension modification process. It's not there's nothing learnable in pooling. Like convnet is a learnable thing. It's the size of the filter, the values of the filters are learnable parameters. But in pooling is just size manipulation. So for example, what you want to do is you have this kind of like 224 by 224 by 64 here, and you want to downsize your dimensionality to half. Then what you can use is use something called pooling. So how do you use pooling? So or pooling or downsampling is the same thing. How do you use pooling? So something called max pooling is how this works is you have 2x2 max pool, 2x2 max pool, or we call this filters, but it's the values of the filters is unlearnable. So you have 2x2 max pool and stride 2. We usually use the same stride as the size of the filter when you're using pooling. So 2x2 filter, then stride 2. So what you do is max pooling is you take a look at these 4 values and take the largest value here, which is 6. So 6 here. You look at this part, the large size is 8, so 8 here. Here, 3, the max size is 3, 4, 4. So that's how you do max pool. And obviously, average pool would be just averaging these values, like 1 plus 1 plus 5 plus 6, then divided by 4. 2 plus 4 plus 7 plus 8 divided by 4, So that would be average pooling. And so max pooling works pretty okay. So like what it says is that in this neighborhood, in this patch, you only want to take the strongest signal and then move on to the next patch. You only take the strongest signal. You ignore the noisy, small signals. So that's what max pooling is. So as we've looked at the preview, the typical ConvNet usually goes through like conv nonlinear, occasional pulling to downsize your dimensionality, then conv value, pull conv value, and then at the end you would have to have a fully connected layer at least once so that you can do a classification, because you need to convert the size of your, so it will be like there will be some latency like activation map, 3D activation map here. You need to convert that into a into like a vector that whose size is the same as the number of alpha classes. So you need at least one fully connected layer. All right, summary. So convnets usually stack conv, pulling, fully connected layers, and occasional nonlinear activation. Obviously, there should be nonlinear activation function. And yeah, trans tower. This is kind of like old principle because people do not use convnet as frequently or as often as the old days because of vision transformer. But trends are smaller filters. As I said, we usually use 3x3. We don't use 5x5, 7x7. We usually stick to 3x3. We use small filters and deeper architectures like ResNet 50, ResNet 100, something like that, ResNet 150. And trends are that we do not use pulling options. So instead of using pulling, we can use striding of 2 or striding of 3 to downsize the dimension. So it's just like if you want to downsize your spatial dimension, you can just manipulate the stride without actually pulling anything. So that's, one way to look at it. Right. So moving on. Just it's like side note on 1D convnet. So convnet, we've so far only talked about 2D convnet, but you can totally use 1D convnet. As I've said, as if you're using like DSP, you have like a one-dimensional signal, like a sequence. It's a sequence, right? You have a sequence, and you can use filter 3. So it's no longer 3x3 because it's one dimension. So it's just 3. With stride 1, then you would have 3 here, 3 here, 3 here, here, here. If you're using filter 3, stride 2, then it's here, here, and here. So, and with padding, if you use padding, then your output dimension would be the same as your input dimension. So you can use this kind of like 1D convnet. 1D convnets are actually still pretty often used, as opposed to like how people use vision transformer on images rather than 2D convnet. 1D convnets are still kind of like, often used to handle like very, very long signals like voice or audio, because the audio usually have sampling rates of 128,000, something like that. So it's a very, very long sequence. So it's better to use convnets rather than like transformers. Transformers cannot handle 100,000 sequence length, right? So one of the very, very first paper that used 1D convnet on like NLP test, which is document classification, was like way back in 2015. I'm not sure, 2014, by Yoon Kim, who's now an MIT professor. So he was, I guess, officially the first guy, the first person to use convnet, 1D convnet on text to do like text classification, which was a pretty neat idea, because if you think about it, language has some local dependency. Like the first word and the last word in your sentence usually are not as correlated as the words that is right next to your current word. Make sense? So you can totally use convnet on text, but nowadays everybody uses transformers, so this is like old stuff. If there's 1D convnet, then there's obviously 3D convnet. 3D convnet is you can use 3D convnet on not images, because images are 2D information. So 3D images, which are videos, or video, because videos have like a temporal axis. So videos, you can think of videos as like a sequence of images, and sequence meaning like on over time. So that's, you can use 3D convolution on videos or actual 3D spatial images like CT scans, for example. CT scans is a 3-dimensional information. So you can use 3D convnet on 3D, like CT scans as well. So CT scans or videos. And obviously the filters now have to be actually 4-dimension, because now there are 3 like height and width and length And then there's like channel. So the filters has to be 4-dimension now. So if you think about 2D versus 3D, two-dimensional ConvNet goes like this, like it goes across the images. In 3D ConvNet, it actually goes like this, like 3D wise. So it's very computation heavy actually. So you like people don't use 3D ConvNet very often because it's so computational heavy. Right, so that's all the ConvNet stuff so far. And the training techniques, we'll have to look at some of them, starting with batch normalization. Anyway, so before we start with the training technique, any questions so far? Right, I guess 그럼 글로벌 디펜던시가 더 클 땐 뭘 사용해야 되나요? Excellent question. 글로벌 디펜던시가 더 클 때는 트랜스포머를 사용하면 됩니다. 트랜스포머는 attention, 우리가 아직 트랜스포머를 안 배웠죠. So the question is it's a very nice question. Question is, then what kind of architecture can you use when the data is more heavy on the global dependency side rather than the local dependency side? So we can't use ConvNet in that case. So what should we use? And the answer is transformers. So we're going to learn transformers anyway, but to give you a preview, transformers don't have any assumption as to how let's say how the elements in your data interact with each other. So when I say elements, it's like pixels in your image or tokens in your text or pitch in your audio. So they're like all set, right? So like image is a set of pixels. Text is a set of tokens, and audio is a set of pitch, right? So if you think about data as a set, then the set consists of elements, right? And the good thing about transformer is it doesn't have any assumption as to how the elements in your set interact with each other. ConvNet has a very strong assumption. ConvNet has an assumption where the elements in the neighborhood interact with each other, but not with the other stuff. So that's a local dependency. But transformer has no assumption at all. So it's a very large, it has a very large degree of freedom compared to ConvNet or RNN or anything else, So that's why it's so flexible, and that's why you need a lot of data to train it, because it makes no assumption. So you need to give a lot of data so for the transformer to pick up the pattern. But ConvNet has a very strong assumption, so you only need to give like very few number of samples to train ConvNet, because your hypothesis space is way smaller than transformer. If that makes any sense at all. All right, cool. That was a nice question. So yeah, training techniques, normalization. So before we go into like batch normalization, I'm assuming that everybody knows what normalization is. It's like high school stuff. So if you think about like a Z normalization or Gaussian normalization, what you do is you usually take or subtract from your data, you subtract the mean and then divide by the standard deviation. So that's Z normalization, right? So it's usually a good idea to normalize your input to this so that you actually like bias is no longer like a big issue, and your model like behaves nicely during training. And yeah, but it's in order to do Z normalization, you kind of have to assume that your data is like normally distributed, but that's not like, or features are normally distributed, but that's another story. So that's normalization. And another thing called something that we should note is something called distribution shift. Like, people who research on like out of distribution detection should be very familiar with distribution shift. So if your test data, for example, if your test data are very much different from your training data, for example, when you train your model on MNIST, but you suddenly test on Cypher10, then it wouldn't work because your model was not trained on Cypher10, it was trained on MNIST, and it cannot generalize to Cypher10 all of a sudden. So, machine learning models are usually very vulnerable to distribution shift. This is what distribution shift is. Your distribution of test data is suddenly very much shifted from your training data distribution. Right, so, and now we go to something called internal distribution shift. So internal distribution shift, what it means is the k-1's layer, the previous layer's activation or output, it's the same thing, is the next layer's input. This is like common sense, right? So your previous layer's output is your next layer's input. Parameter update, which means that you update your parameters with backprop, right? So backprop means that if you have like this is your input, this is your input, and this is your output, then backprop means you update parameter here, then here, then here, then here, and then here, right? You start from the top and then go all the way to the bottom when you do backprop update. So parameter update changes your previous layer's activation. So the parameters in this layer will change, which means that this output will change as you update your parameter. So that means that your kth layer, which is your next layer, needs to adapt to new distribution after every update, because this was updated. So it goes from here, like backprop goes like this. So this guy's updated, then this guy's updated, then this guy doesn't know that this is updated. So all of a sudden, this guy needs to adapt to the new updated or new shifted distribution of output from the previous layer. So that's what internal distribution shift is. So that's a problem. That's what usually makes like a training process a little bit like difficult for the model for the model, basically, because when you do a backprop, it changes the internal distribution. So it causes internal distribution shifts. So like layer K needs to look at this and then adapt to it every single time you do like a backprop. So it's making the optimization process or the learning process a little bit unstable. So the batch normalization was a technique to cope with that, and it was proposed back in 2015, I think. And batch normalization, I don't think people use it. I don't think people use it as often as before, like back in 2015, 16, 17, maybe up to like 18. People use batch normalization very heavily, but these days not so much. Or at least that's my impression. So what the idea is that batch normalization idea is that let's remove internal distribution shift, because this was a problem for your training your model. So let's remove internal distribution shift. And how do we remove it? How do we remove it? Which means it's pretty simple. You just normalize the output of your layer for all the layers. For all the layers, you normalize the output. Then your output will always have the same distribution, so that your next layer will be very comfortable, taking it in and then updating it at each iteration or at each backprop. So that's the whole idea. So normalizing the output of your layer, which is just simply you take the mu, you take the sigma or the variance, and then you do this Z normalization. And then here, you don't finish here. You actually do a scale and shift. So this is the normalized output. So this is I forgot to mention this. So this is you have a mini batch, a value of X, and then what you do is you use some function called BatchNorm function, which is governed by two parameters, gamma and beta. So this BatchNorm function, what does it do? What it does is you take the ith input, you do a BatchNorm over it, which is simply calculating the mean and standard deviation, normalize it, and then scale and shift. This is where gamma and beta, the learnable parameters, come in. So if your gamma is the same as sigma, and if your beta is the same as mu, then this y is actually xi. So it's not doing anything. So basically what we're doing is we've normalized it, but maybe that's just too much of a constraint, because normalized value usually has to follow like this, right? So that's maybe a very harsh constraint. So we actually give some flexibility to move around. So that's where gamma and beta comes in, right? So yeah, we want to keep the same distribution, output distribution for every layer, so that the training process becomes way smoother and more stable. Right, so batch normalization was the very first normalization technique that was proposed, okay, way back in 2015. And I've just gave you an overview. You take the mu and sigma, and then you normalize, and then you do, where did it go? Yeah. If your zero mean is too hard of a constraint, that is why we do this. We scale. Scale is the like multiplying with a real value. Scale and shift. So as I said, if the scale is the same as sigma, and if the shift is the same as mu, then it'll just be an identity function. And so that was it. Very important stuff. Probably why people don't use BatchNorm very often these days is the different behavior between training and testing time. So if you look at here, how you calculate mu and sigma, the mu and the variance, or mu and the standard deviation, is taking a mini batch. You just normalize over the mini batch. So you take all the samples from your mini batch, like this is the size of the mini batch. You take all the samples from your mini batch, and then you normalize it, and that's how you get mu, or mu j is the jth feature. So this is so you need to look at all the samples in your mini batch and then average it to get this, and then do batch norm finally this. So it depends, this whole thing depends on the size of your mini batch and what's inside your mini batch. Like theoretically, when you do stochastic gradient descent, your mini batch should only consist of IID samples. The samples in your mini batch should not have any dependency amongst them, which is not always, like not always well kept, but still, like, so anyway, so the performance or the quality of your batch normalization depends on what your mini batch is, basically. So that's why it doesn't work in the same manner between like training and test time, because in training time you have training samples, but in test time maybe you only test one sample at a time, so there's no mini batch at all. Like you can't, sometimes you only test one sample at a time, you can't have a mini batch, meaning that you can't do batch normalization. So you can't do this at test time. So what you end up doing is you do a running average of values seen during training. So when you train your model, you keep your mu's over many iterations, averaging, like, running average for mu and sigma, and then you keep that value around, you keep those mu and sigma around, and then you use them in the test time. And that is usually a very, it's like usually a source of all the bugs that happen in deep learning models on deployment. So that's why people don't usually, like batch normalization. Even the code for this is back in the TensorFlow days, but the TensorFlow code for batch normalization was like not good, basically. Right. So yeah, where this is just another technicality. Where do you use batch norm? Do you use batch norm before nonlinearity or after nonlinearity? But this is the kind of old news, so we can skip this. Right. The problem is, behaves differently during training and testing. This is a very common source of bugs. So batch norm, that was batch norm in theory. Batch norm for confidence a little bit different. So in batch norm, so far what we talked about is this is the size of the mini batch. This is the size of your feature or dimension of your input. And you normalize across, you average across your mini batch. So n becomes 1, right? In ConvNet, there's n, the size of the mini batch, and there's h and w, which is spatial dimension. So they are all collapsed into 1. So you average across n, the h, w, you average all across them. Only the channel dimension survives. So that's how you use batch norm in ConvNet. And there's something called layer normalization. This guy was actually proposed after batch norm to use normalization in RNN, but now people use layer normalization in transformer all the time. So transformer uses layer normalization. So layer normalization is a little bit different. It normalizes across dimension, feature dimension, not n. The d becomes 1, right? So so the layer normalization does not depend on anything that has to do with mini batch. It doesn't care about the size of the mini batch. It doesn't care about what consists of mini batch. It doesn't care anything about how your mini batch, what your mini batch is. So that's why it has the same behavior at train and test. So you just like it's way easier to handle. Way like you don't care, you don't have to pay too much attention to how you use it, as opposed to batch normalization where you have to have like a running average, and it's like pain in the ass. Right, so that's layer normalization. And there's something called instance normalization, which is used in like style transfer, like in StyleGAN. StyleGAN is something called adaptive instance normalization, ADA-in. So instance normalization is like kind of like still a thing in style, like like extracting style information from each of your sample, basically. So style instance normalization, it averages across H and W. So each sample's characteristics survive, and each channel's characteristic survives. It's the spatial dimension that actually is collapsed into ones. So that's instance normalization. Oh, there were some questions. Didn't see that. From Aldo, what is the alternative to BatchNorm used nowadays to prevent vanishing and explode? Actually, BatchNorm, I don't think BatchNorm has anything to do with vanishing exploding gradients. Or maybe indirectly, but BatchNorm was not proposed to directly cope with vanishing or exploding gradients. BatchNorm was proposed to cope with internal distribution shift. So your question is a little bit like misplaced, but people, as I said, people use layer norm very heavily in transformer. Transformer actually depends on layer norm, and I don't. Yeah, batch norm no longer, not so much. 한규원님, variance에 더해진 epsilon을 일정한 작은 양수로. Yeah. I think what you mean is right here. Yeah, this is just to keep the like underflow overflow problem. Like if variance is so small, if variance is like near zero, then this becomes like kind of like infinity. So you don't want that to happen. So that's why epsilon is like some value, like some 0.001, something like that. Good question though. Right, there's a like graphical depiction of different normalization techniques. So batch norm, so it's a 3D, it's a convolutional batch norm. So there's like H, W, N, and C. And unfortunately, because we can't visualize 4 dimensions, so H and W are collapsed into a single dimension. So what happens in batch norm is you collapse N, H, and W all at the same time. So the only thing that survives is C, right? This is the only thing that survives. So each dimension in C will have one value that is like collapsed. So like each C will have its own value. Layer norm, on the other end, collapses this guy, the channel dimension, and each sample survives. So each sample will have different values. And in instance norm, each CNN will have some value. Each CNN will have some value, because only the H and W collapses. So that's the difference between different normalization techniques. I think we're off to dropout, right? So dropout is another, you can think of this as like a regularization technique that was proposed way back in 2012 or 13. I'm not really sure. It's like very, very, very like one of the first techniques that was proposed at the birth of like, oops, where are we now? At the birth of like deep learning. So what happens is in dropout, you set a certain certain probability, for example, like 10%, and you drop them, or you mask them out. You put them, you set them to 0. So if you have like 2 hidden layers, one and 2, each hidden layer has 5 neurons, then with like, for example, like 20% probability chance, you would mask randomly. You would randomly mask, like this guy has 20% chance to become 0. This guy has 20% to become 0. This guy, like every neuron has like p chance to become 0. So randomly. So that means that at some point this could happen. Like they'll be masked out. And you'll only be able to use subset of neurons to process the input information. Oh, there's a serious lag. Okay, this is not good. Yeah, okay. Sorry, yeah, the internet problem. Anyway, so that's what dropout is. And you can think of this as kind of like an information bottleneck. When we talked about information bottleneck in the autoencoder, right? You have a narrow bottleneck, you have narrow channel where you can put your information through, and that causes the model to learn only the distinguishing feature, right? Kind of like that. It's not exactly the same thing because the channel changes dynamically at each iteration, but like kind of like you have a if you have like a large capacity model, then you would like to sometimes constrain its capacity so that it learns, like it becomes more robust to in the test time, basically. Right. So dropout, that's dropout in general. Dropout in ConvNet is a little bit different. You can drop random portion of your output map or activation map, or you can actually drop out the entire activation map. Like if you have 6 activation maps, then you can just maybe like mask out 2 or 3 or 1. It's just random. You have some p equals like some x%, and then you apply that x% independently to each activation map, and then sometimes they will be zeroed out. And in the extreme cases, sometimes you like drop the entire layer. It's called drop layer. And yeah, there were like a lot of people like researchers focused on how dropout behaves and why dropout helps and that kind of stuff. But dropout is no longer, just like BatchNorm, dropout is no longer like heavily used. Some people might use it when you have like very small amount of data and you want to like avoid overfitting your model to the data, then you can use like dropouts. But people don't pay too much attention to dropout or any regularization technique these days, because people are interested in like large language models where you have almost infinite data. If you have almost infinite data, you don't have to regularize your model, because regularization is a technique that you use to avoid overfitting. But if you have infinite data, it's kind of like hard to overfit to infinite data. Right, so I think we're right on time, actually. Yeah, I speed things up a little bit, so I guess we're right on time. So CNN architecture, some of the well-known CNN architectures are like these. So starting from 2012, this is where people started to use convnets. So Lin, like these are like classical models, probably using, I don't know, SVMs or random forest or some other models. But then 2012 is where we started using like stacks of convnets. So AlexNet, ZFNet, VGGNet, Google like Lunet. So this is probably like, this is Inception version 1. ResNet, not sure what this is. Not sure what this is. Like, I guess this is squeeze and excitation net. I'm not really sure what this is. Not sure. Yeah, this is human performance. Anyway, even like starting from 2015, we were already outperforming human performance. So only 3 years. It took only 3 years. Starting from 2012, which is the birth of deep learning. 2012 to 2015, it took only 3 years to outperform humans. If you compare that with 2010, which is like 28% error rate, which is like 70% accuracy, this is like a big jump here. So we won't be looking at all the models. I think I prepared like VGGNet, Inception, and ResNet, but VGNet, we can skip VG. Oh, we actually start with AlexNet, but yeah, we will skip AlexNet. VGGNet, maybe we can skip this as well. And you can see here, like there's like 2 versions of VG, like VG16, VG19, and it has all. If you look at all the small numbers here, it's using only 3x3. So look, if you look at AlexNet, it has like 11x11, 5x5, 3x3. So it used different like filter sizes. But starting from VGG, we only stick to 3x3. We don't even use 5x5 or 7x7, right? We only use 3x3, and increasing the size so that we have like larger receptive field. And then there's like a couple of fully connected layers. So this is actually, if you use fully connected layers before softmax, so softmax is like, this is necessary. This is necessary to do ImageNet challenge, because ImageNet requires you to have a 1,000 dimensional output, 1 dimension per class, right? But aside from that, if you use like these models, I mean these layers, like fully connected layers, then it will constrain your model to only work with certain dimension, no, certain input dimension, like 128 by 120 by 3 image, something like that. So starting from inception net, we no longer use fully connected layers. We only use it at the end for classification only. And before that, there is 0 FC. Actually, maybe I'm wrong. Maybe there's like side FCs here. So maybe, okay, so forget what I just said. Maybe that applies to ResNet. So VGNet is this is VGNet, and then InceptionNet is probably the first one to use like repeating component. Repeating component meaning this is a single inception module, and you use it all the way, like here, 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 here. Like you use the same architecture over and over again. And this is employed in transformers, because in transformers, you have the same architecture, stacking of stacking of stacking. So this is probably why it's called inception, because you use the same architecture over and over and over and over again. And each architecture has a little bit of like different paths, like one by one here, 1 by 1 followed by 3 by 3, 1 by 1 followed by 5 by 5, 3 by 3 max pooling followed by 1 by 1. So there's like different channels to consume or process your input, and then you pull it, and then you pass it to the next guy, and you do the same thing, pass it to the next guy, next guy, next guy, all the way to the top. And then you do 1000 class classification. Oh, it is no FC layer. Yeah, so no FC layer, which means that it can consume any dimensionality image. It could train. You can train InceptionNet on 128 by 128, but at the test time you can use 256 by 256. It'll just behave in a different way, but it'll still work. It's not going to give you like a syntax error or something, or runtime error. So that was LUNet, GoogleNet, or Inception version 1. I think there is like Inception version 4 at recent. Like they have like they kept iterating on Inception version 1, 2, 3, 4, and I don't think there's 5. So I think they ended up in version 4. All right. Moving on to the most important part today, ResNet. So ResNet proposes something called residual connections, which is probably one of the most important concepts in deep learning. Very few things survive. Like this was proposed in 2015, and things that were proposed in 2015 rarely survives today. People don't use techniques that was proposed in 2015 today. Kind of like, like people don't use BatchNorm that often, or people don't use Dropout that often. That not very often, but people still use residual connections everywhere. Even in Transformer uses residual connections. So it's a very, very important concept. And this was the very first paper that was able to use more than 100 layers. Because if you look at AlexNet is how many layers? It's 1, 2, 3, 4, 5, 6, 7, 8, maybe 8. Yeah, like 7 to 8 layers. VGG19, like 19 layers, is 16 layers. Inception was I don't know, 1, 2, 3, 4, 5, 6, 7, maybe 20 to 30 layers at max. 20 to 30 layers. Yeah, I would say like less than 30 layers or so. But ResNet was the first model that was able to go beyond 100 layers, even like 1,000 layers. This was like the very first model, very first architecture that was able to use as many layers as you wanted without sacrificing performance. So that's the most important message of ResNet. So yeah, it swept all classification detection competition way back in 2015. And its architecture looks like this. So it starts with an input and then like initial massage into 7 by 7, and then you have repeating architectures, here, 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 and there's like way many more repeating architectures. And you use 3 by 3 everywhere, 3 by 3, 3 by 3. It's all 3 by 3, 3 by 3. And 64 filters, and suddenly 128 filters. So what this means is using stride 2. So stride 2 means you are decreasing the dimensionality of your spatial dimensionality of your input. So it's you don't see any pooling here, right? There was pool here, there was pool here, like here everywhere. There was pool here. So VGG had pool, AlexNet had pooling layer, Inception had pooling layer. ResNet doesn't have a pooling layer. There's only one final global average pooling, which is kind of like it's not max pooling, it's something else. So there's no pooling anywhere in between. It only uses different stride sizes to manipulate the input side, the dimension, the spatial dimension. So that's another like a characteristic. So if you look at it, what residual connection is, it's there's an input, then there's an output, and well, actually, this is the output. So this is an input, there's an output, and there's a skip connection or residual connection. So this is a standard conv, like conv nonlinear, and they put another conv here for some reason. And then that is usually the output. But on top of it, in addition to that, there's a skip connection where you put signal from X to the final output directly. So there's like plus X here. So without this, it would be just FX. But with using this skip connection here, you're propagating your signal directly to the final output. So there's plus X component here. So that's ResNet. So the intuition behind ResNet is very interesting. What happens when we continue stacking deeper layers on a plane convnet? So plane convnet is conv nonlinear, conv nonlinear, conv nonlinear, conv nonlinear, like, repeated conv and nonlinear. So if you just keep stacking that kind of like conv and nonlinear all the way, like maybe 50 layers or 100 layers, what happens? So that was the question. So here you can see that this is as you train, this is your training error, this is your test error, and this is your 20-layer model architecture, this is your 56-layer architecture, right? Gradient vanishing. That wasn't a question, but sure, you can, yeah. If you want, you can answer. So you can see that training, so 56-layer, 20-layer, 56-layer, 20-layer, and you can see that here, as you training error and test error, if you look at both at the same time, what's happening here is that this guy and the larger layer or like a deeper layer, which has more capacity, is underperforming this guy, right? So is this like, can you call this a overfitting or underfitting, or what's happening here? Can you call this an underfitting or overfitting? It's neither, probably, right? Because if it's overfitting, then you would see this guy being here. At least the training error should be lower than this guy, because this is a larger capacity model. It has more layers, right? Yeah, this is not underfitting. This is not. Oh, yeah, okay, yeah. That technically, yeah, I guess we can call this an underfitting. So, nah, not really underfitting, because so if you think about the concept of overfitting versus underfitting, over versus overfit versus underfit. Underfitting is when your model is not large enough. It doesn't have enough number of parameters, or it doesn't have enough capacity to learn from data. So that's how you overcome underfitting, is increase the size of your model. But that's not what's happening here, because your model is already larger than this guy, right? So this is not underfitting. At least we know that this is not underfitting, because the larger model is underperforming lower, like a smaller model. So simply, if it was underfitting, if this was underfitting, then increasing your model should actually have helped for training error to go down. But this is actually increasing, right? Right. Yeah. So you can say that it's not. But well, before getting to that, so you can see that it's not overfitting or nor underfitting. If it was overfitting, you would see training error here and testing error here. That would be overfit. That would be overfitting. But the training error is here, test error is here, so it's not overfitting nor underfitting. Right? So what is this problem? So a lot of people said this is vanishing gradient. Maybe someone care to elaborate why so many people just answer vanishing gradient. Why not exploding gradient? Right, gradient keep multiplying, but it could very well lead to, exploding. High complexity, yeah, I mean, it is high complex, but that's quite not the source of the problem here. I think it could also be exploding. Right, it could explode. It could become smaller or larger. So if so let's like if someone can just succinctly say where the problem lies, this is nor underfitting or overfitting, right? So how would you what is the problem that's happening here? If it's not underfitting, if it's not overfitting, then what's the source of the problem? All right, so many people are answering, so I can't really read them all at the same time. Naufal. I think Naufal has the most accurate answer so far. Deeper model is harder to optimize. Yes, that's the source of problem. I mean, vanishing gradient, exploding gradient is kind of like like a detail. The the core intuition is that it's just harder to train. So that's why before ResNet, people were only able to stack up 17 layers, 19 layers, maybe 20 layers using ReLU, because ReLU was another thing that enabled us to use larger models, like larger layers. But that could only get you up to maybe 20 layers, like maybe 15, 20, 30 layers. But ResNet was able to get to 1,000 layers without degrading performance, maybe marginal degrading performance. So it's just harder to train. 커패시티가 큼에도 fit 자체가 되지 않습니다라는 것도 이제 맞는 말인데 그게 정확한 말은 아닙니다. 커패시티가 크다는 거는 이제 이게 그 사이드로도 클 수가 있기 때문에. No, it's not. It's not lack of data set. It's not lack of data set. It's just purely optimization problem. No matter so before ResNet, no matter how much data you had, you couldn't increase your model up beyond certain sizes. Right. So it is vanishing and exploding gradients. Local minimum. I'm not sure what local minimum is. The parameter increases and it becomes difficult to no, that actually, so the succinct answer is deeper models are harder to train. And why is it harder to train? Because gradients become larger or smaller depending on the data, depending on your architecture. So vanishing gradient or exploding gradient is kind of like the right answer, but the like high level intuition is that it's just deeper models are harder to train. And the reason is that the gradients become smaller or larger. It doesn't always get smaller, it doesn't always get larger. We don't know what would happen. It depends on like how you initialize models and what kind of data you're training on and what kind of like optimizer you use, like SGD or Atom or whatever. So that was the intuition behind Cunningham, who was the first author of ResNet. And question: is there a depth depending on the complex? Is there depth depending on the complexity of data? You mean like, should we increase the size of the? Should we increase the size of the layers? Like, should we increase the number of layers depending on the complexity of data? Can residual is there a depth dependent? I'm not sure. So yeah, if your data is complex, then you should have powerful model to manipulate or distort your latent space as much as necessary. So I guess that's a yes. Question from Woo-jung. Can residual connection prevent gradient exploding? I would say so, yes. So the intuition is really actually simple, because what happens is that if you just use plain X, if you use just plain X layers, which is just, any convnet or any fully connected at any RNN, whatever. Actually, RNNs can't use residual connection, so that's a different story. Anyway, so if you use old deep learning without skip connection or residual connection, then this is your output. HX is just simply your output. But if you use residual connection, then what happens is that your output is now fx plus x. Fx plus x. So it means that if your model is already doing a good job before this layer, there should be a lot of layers here, right? There should be a lot of layers before this layer, right? So if before this layer it was already doing a good job, then fx doesn't need to do anything, because X is already a very well structured, very like well manipulated vector representation of your inputs. So it's just ready to do whatever test, like classification test, regression test, whatever test you want. It's already ready. It's already there. So this additional fx plus x, this additional layer is just redundant. It's just unnecessary. So what happens is that before residual connection, this layer had to learn identity function. This layer, if x was already good enough, then hx need to be the same as x, because x is already good enough, right? Then this function had to learn identity function. But this guy learning identity function is pretty tricky. It's very difficult, because identity function has a very weird diagonal shape, right? But if you have a skip connection, then fx just needs to be 0 if x is already good enough. If x is already good enough, then fx just needs to be 0. Then hx becomes x when fx is 0, right? So, and this function being 0 is way easier than this function being identity function. So that's the idea behind skip connection or residual connection. You just need to learn the difference. 차분이라고 하죠, 차분. 이제 그 차분만 배우면 된다. 내가 이미 x가 다음 x로 갈 때 필요한 그 디퍼런스 프라임만 배우면 된다라는 게 ResNet의 핵심 원리입니다. You just need to learn the difference. You keep the core information and you just gradually manipulate it so that you have the final representation vector that is ready to do whatever task you need to do, and you just carefully or incrementally manipulate it using only the difference. So this function now needs to learn the difference, which is very small value. So when you say that can residual connection prevent gradient exploding, I would say probably. I haven't thought that through yet. Usually, if X is already good enough, all the signals would just, go through here. So, am I making a correct assumption? Yeah, I'm not. Yeah, I'd say I'm not 100% sure. It's just, you just set the train, you just set the functions to learn a way simpler objective than before. It's like layer-wise ensemble. Layer-wise ensemble. What does that mean? Layer-wise ensemble. Not really sure what you mean. Ensemble, you have like a sum of two functions. Yeah, I guess you could call that. But yeah, it's more like you just learn the difference. It's like a 이제 그 차분값만 배우는. 그래서 이게 이제 나중에 뉴럴 OD로 이어지는데. Well, I mean, yeah, we'll have some time to talk about neural OD. But anyway, so yeah, so the paradigm is like changing from before. Before, without residual connection, the desired output should only come from this guy. So this function should take this, massage it, so that you could have a desired output. But now this function doesn't have to massage the X to desired output from scratch. It just needs to learn the difference because there is this foundation which you can use anyway. In the end, you just need to learn the difference. So it's like a paradigm shift. Right. So yeah, use layers to fit the residual. Maybe you can think of this as kind of, not ensemble, like a boosting. If you know what boosting is, we talked about boosting very briefly in the second lecture, I think, like bagging and boosting. Boosting is where you use like a sequence of functions, sequence of weak learners to fit the difference, fit the error bit, basically. So this kind of like that. You just fit the residuals. That something that couldn't be done in the previous layer. Like you still have errors that is left over in this layer. So that error is controlled by this guy. Hopefully that makes sense. The analogy between ResNet and boosting. Right. So yeah, the specific architecture of ResNet was like this, exactly like this. So 3x3 conv, ReLU 3x3 conv, and then then you do a skip connection here. And you repeat this every single layer. And sometimes, as I said, you would do like stride two here and there. And when you do stride two, you increase the number of filters from 64 to 128, 128 to 256, 256 to 512, all the way. And then you are in the end, you do something called global average pooling, GAP, which is just you collapse all the dimensionality and you're left with only 512 dimensional output. So after this you have 512, if I remember correctly, like 512 dimensional image representation vector, and then you convert it to 1000 classes, and that's how you do ResNet based image classification. Question from 박재현. hx equal 2fx plus x 같은 경우 차분을 강조하는 경우도 있네. So the fx needs to learn like even smaller difference than before. 그러니까 이제 1fx보다 2fx로 하면 fx가 반만 배워도 된다. 뭐 이런 아이디어인가요? 그렇게 할 수도 있을 텐데 그게 도움이 될지는 잘 모르겠습니다. EFX 대신에 E 대신에 뭐 AFX를 할 수도 있지 않을까요? 그리고 A를 러너블 파라미터로 넣을 수도 있을 것 같은데 그런 거를 시도한 사람들이 있었는지 모르겠네요. 근데 굳이 그렇게 안 해도 그냥 스킵 커넥션만 붙여놔도 굉장히 잘 됩니다. 이제 100레이어를 붙여도 굉장히 잘 되고 이제 첫 논문에서는 1000레이어까지도 가고 막 그러는데 1000레이어를 가도 거의 이제 그 디그레데이션이 없다. 라고 이제 했습니다. All right, so that's it. We've already covered stride 2. And yeah, no FC layer means that it can handle arbitrary input image size. And yep, that's it. Yeah, this is basically it. So there's a lot of different confident architectures like VGG, ResNet, Inception version 1, 3, ResNet 50, Inception version 4, and they have different like number of parameters and different number of operations, the flops, and it's just a chart for comparison between different architectures. So this is it for the ConvNet, and as before we end, so we're going to do a poll on when to start the project number 1 next week. So what we will do is that we will have a session for describing the specification of project 1 either on Tuesday or Thursday. So there was some people who asked for doing a project on weekends, but we decided that's probably not a good idea because we will do a full 1.5 hour description of the specification either on Tuesday or Thursday, which is actually the class day basically. So we know that everybody doesn't have any conflict on that day on 10:30 to 12 on Tuesday or Thursday because that's the original class day. If we set it to weekends, some people might have class schedule conflict, so we can't do that. We can't accommodate to all the different cases of schedule conflict, but at least we know that 400 people has no conflict on 10:30 to 12 every Tuesday and Thursday because that's a class day. So it's either going to be Tuesday or Thursday. So that's going to be the poll. So after this, we'll do a poll, and you should vote basically whether you would like to have the description, whether you'd like to have the spec description, spec announcement on Tuesday or Thursday, and we'll do a 1.5 hour spec description or spec announcement. And after that, you will be given 24 hours to finish your project 1 and then submit. So that'll be it. So we'll go with the voting, the voting thing on, we'll announce the voting thing on Classum. So right after this. So the voting will end on midnight tomorrow, which is like 0 a.m. Thursday. So please vote. If you want to make your voices heard, please vote. Right, any questions so far? About ConvNet, you know? So this vote, yeah, this vote is for only project 1, yeah. All right, thank you guys. And if you have no more questions, yeah, we can, yeah, we're going to give until 10:30 on Friday or Wednesday to finish. Yep, 10:30. Actually, it'll be 12 because the project announcement will take 1.5 hours from 10:30 to 12, and then starting from 12, you'll be given 24 hours. 그렇죠. 다음날 오전 11시 59분인 거죠. Okay, then hopefully everybody so the spec will give you a very weird thing that you cannot download from the internet. It's not going to be like ResNet 50. It's something that you have to build on your own, like 3 layers of ConvNet with some filter size, some stride size, some padding size. So you should really be familiar with what I've told you guys today. All right, thank you guys. If you have any question, please post them on Classroom. And please attend this Thursday's practice session, unless you're already familiar with content. All right, thank you guys. Bye-bye. 네, 감사합니다. Thank you. 감사합니다. 네, 감사합니다. 네.